Okay, welcome to our. Oh, okay, I'm not on the homepage. Let me actually go to the homepage. Okay, welcome to our SMO senior live stream. Okay, this time it seems that there's less delay in the stream for some reason. Okay, maybe I'm wrong, maybe I'm right. But it seems that there's only like a 10-second delay in the stream. Okay, anyway, so how do you feel about this SMO senior paper? Now, hopefully, right, you found it somewhat okay, because if you found it somewhat okay, that means that you are already doing a lot better than everyone else. Because it's guaranteed that people will find this to be pretty difficult of a paper. I want to make a claim already. I want to make a claim that just with probably a single digit number of points, you can actually get into round two. Okay, that's my claim. I might be wrong, but who knows? Okay. So let's go through the question. Question number one. Suppose that a fair four-sided dice with faces labeled 1, 2, 3, 4 is rolled twice, producing outcomes B and C, and P be the probability that this quadratic equation has two real and distinct roots. This means that my discriminant, the B squared minus 4AC term, must be bigger than 0, right? Okay, so what's the probability that B squared is bigger than 4C? What we can do is that we can just list out the possibilities. So for example, B equals to 1. This is never possible. B equals to 2, then you can see that, oh, I just need this to be less than 4, right? But C needs to be less than 1. Also cannot. B equals to 3, this needs to be less than 9. So C has two possibilities. C equals to 1 or 2. And then finally, B equals to 4. This has three possibilities. C can be 1, 1, 2, or 3, like this. Right? So there are a total of 5. So if there are 5 possibilities, right, and we know that the total should be 4 times 4 equals to 16, then this is P. So then 1 over P round up will turn out to be the answer of B, 4. Okay, next one. Question number 2, a string of length L is wound uniformly around a cylinder of circumference 5 cm exactly 4 times. Find the value of L round up. So first we can split it up into 4 parts, right? So each part, it looks like this one go to the back of the cylinder, come to the front of the cylinder again, and go up again, so on. So kind of looks like a sine wave, right? Except that actually this is something in 3 dimensions. Okay. So for one single part here, what we can do is that we can try to actually unravel it. So how can we unravel? We unroll the cylinder and we can make it a rectangle. Now they tell you that the circumference of this cylinder is equals to 5. So then we can label one of them as 5. This entire height is 48. So when I cut it into 4 parts, one of them will be 12. Right? And then the result is that the curve that is unwound will be just a straight line connecting the two endpoints together. Now obviously that means that the length is 13. Right? So therefore, if I do this 4 times, the final answer it will be B, 52. Okay. Next question. Already we have a question that looks very scary. Given that the minimum value of this is pi to the power of a over b. So what's happening here? There's a tangent inverse of x. There's a tangent inverse of 1 over x. So what you can see over here is that these two things, they're related. How are they related? They are not reciprocals of each other. Because of the tangent inverse, they are not. But rather, they are related by their sum. The sum is always going to be 90 degrees, which is going to be pi over 2. Why is the sum always pi over 2? That's because if you think about it like this, let's say I have a right angle triangle. If this is 1 and this is x, then tangent inverse of x is this angle on top. Meanwhile, tangent inverse of 1 over x is this angle on the bottom left. Right? So therefore, we can see that those angles will add up to pi over 2. Now, and you know that there are angles within, for example, right angle triangle because of the fact that x is bigger than 0. Because x is bigger than 0, each one of this is a positive value, and the tangent inverse has its principal angle from 0 to pi over 2, right, for a positive value. Okay. So now, if I know that's true, how do I minimize the sum over here? Right? So given that, for example, we can call this a plus b. A plus b is fixed. How to minimize a to the power 2048 plus b to the power 2048? It should be when the two of them are equal. It should be when the two of them are equal. Because if the two of them are not equal, then let's say one of them is bigger than the other, then the effect compounded to the power of 2048 will be much more, right, than the effect of just having their sum. Okay? This one is also can be called as the power mean inequality. I forgot exactly what the power mean inequality says, but I believe that it will probably be the sum over 2. So let me write it down. I believe this is the power mean, arithmetic mean inequality. It says that a to the power n plus b to the power n over 2, if you take the, not the square root, the nth root is at least a plus b. This is the power mean, arithmetic mean inequality. So in that case, the equality only happens when a equals b, or when n equals to 1, right? Because when n equals 1, then these two are equal to each other. Okay, so yeah, so it should happen when the two values are equal. So if they are both equal, then each one should be exactly pi over 4. So if each one is pi over 4, then the sum, the expression will be equals to 2 pi over 4 to the power 2048. So if you express it in terms of the result, there's a pi to the 2048, and below there's a 2 to the power of what? So this one I can convert it into 2 squared, right? So 2 squared to the power of this is 2 to the power of 4096. But because of the fact that there's additional 2 here, actually it becomes 4095. Right? So A is 2048, B is 2 to the power of 4095. As a result, when you have this log base 2, right, of B over A, actually that is just log 2B minus log 2A. 2048 is equals to 2 to the power 11. So then answer 4084. Finish. Okay. Now we move on to question number 4. Already, question number 4 is one of the hardest questions in the SMO. In fact, there's many questions which I would consider all very difficult. In fact, question 4 is one of them. The reason is because question 4 feels more like a round 2 type of question than rather a round 1 type of question. So what does the question try to say? For any I, this is true for this sequence of numbers. So that means if I take I equals to 0, I equals 0 doesn't exist because it starts from 1. If I take I equals 1, I get A1, A2, A3, A4, and A5. Add up together is less than 0. If I take I equals to 2, I get A2, A3, A4, A5, A6. Together, their sum less than 0. So what it means is that the sum of any 5 consecutive terms less than 0. But at the same time, the one for behind tells you that, oh, if I take j to be anything, I can get sum of any 8 consecutive. Is going to be greater than 0. Now, immediately, we already know the answer must be finite. Because, for example, if there are hypothetically 40 numbers in this sequence, right? Then the sum of the first 5 consecutive, the next 5 consecutive, the next 5, and next 5, and so on, all these will be less than 0. But then the sum of the 8 consecutive will be bigger than 0, and so on and so forth. All these will be bigger than 0, which is a contradiction. So you already know that the sequence must be finite. And the sequence is finite means that the answer options is one of the other 4. And you can see that it's quite obviously less than 40, which means what? There must be some other idea we have to use for this, right? So let's try to draw them out. Since the answer is at least 11, let's draw out 11 values. Okay, so I'm just going to represent them by circles, so that it's easier to think of them. Now, the sum of any 5 is at least 0. Sorry, less than 0. So the sum of these 5 is less than 0, but the sum of any 8 consecutive is bigger than 0. What does that mean? It means that the sum of any 3 is bigger than 0. Because the sum of these 5 is less than 0, right? But the sum of these 8 is bigger than 0. So if I subtract them, I get that this 3 is at least 0. And this can be done for any group of 3. Let's say I pick this group of 3. What do? I take a look at these 8 consecutive numbers, minus away these 5 consecutive numbers. It will be positive. So we can say the sum of, in fact, any 3 consecutive must be bigger than 0. Okay. What else after I can say the sum of any 3 consecutive bigger than 0? I can go back and do one more. The sum of any 2 consecutive is less than 0. Because here, the sum of 5 is less than 0, right? But then the sum of 3 is more than 0. So if you ask yourself, okay, what happens to these two? They must be negative. Okay, they must be negative. And this can happen everywhere. This can happen here because of the fact that I can do this 5 minus away this 3. Right? This can happen, for example, here because I can do like this 5 minus away this 3. So we can get a conclusion, in fact, that the sum of any 2 consecutive, in fact, must be less than 0. Okay, so now this becomes a very interesting kind of sequence. So 11, is there any contradiction here? Sum of 3 consecutive. Wait, actually, I realized I made a mistake. So I cannot say this for sure for anything. Okay. Where's the mistake from? Where's the mistake from? The mistake is from the fact that I didn't pay attention to, how do I say this? Okay, I didn't pay attention to the number of terms in the sequence. So one of these is wrong. Let me see which one of them is wrong. Huh? Okay, so previously sum of any 5 consecutive is less than 0. Sum of any 8 consecutive. Right? So I can do this all the way. Yeah, okay. The first one is wrong. You cannot conclude this. Cannot conclude. Why the first one is non-conclusive? Because if I choose, let's say, the middle tree, can I say anything about this? The answer is no. I cannot say anything about this because of the fact that this middle tree is not part of a 8 minus 5, right? There's no 8 minus 5 here on this side. There's no 8 minus 5 here on the other side as well. So you cannot conclude that. But once you realize, hey, wait a minute, I'm just missing one on the left and on the right, right? So if I move on to the case for 12, what happens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. In fact, I can conclude sum of any 3 less than 0. I can conclude this. Okay. So if I can conclude this, then what it happens is that I have a contradiction. Because what I can conclude is that, for example, I take this 3 plus this 3. Right? It's more than 0, But if I take, for example, these 2 plus this 2 plus this 2 is less than 0, less than 0, less than 0. So I can get a contradiction over here. Whereas this contradiction, I don't think is possible or... Okay, so this means that 12 is incorrect. Huh? 12 is wrong. So 12 is not possible. Whereas this contradiction doesn't happen for 11 because of why? This contradiction cannot happen for 11 because, as I mentioned before, these 3 I cannot conclude, right? So remember how I concluded 2 consecutive is from 5 minus 3. So if I cannot conclude that this 3 has anything, I cannot conclude that this pair has anything, I cannot conclude that this pair has anything. So although yes, I can conclude that for 12 it is wrong, I cannot conclude that for 11 it is wrong. Now that doesn't mean anything. That doesn't mean that 11 is possible, right? But if you're doing the SMO, of course, you will just put out 11 and move on with your life. Because why would you try to show it's possible? But turns out it is. Let's do a construction. So let's construct that case. We just need these two to be true. So for example, for 2 consecutive, I need to choose maybe one even and one odd. Right? 3 consecutive bigger than 0. So maybe I choose the even number, not one even one, what am I talking about? One less than 0 and one bigger than 0. And here, because it's 3 consecutive, maybe I choose 2 of them bigger than 0, surrounding one of them that's less than 0. Right? So if you construct, probably you think, okay, maybe bigger than 0. Right? So I'll do positive, negative, positive, maybe something like this. And I'll do positive, negative, positive, maybe positive, negative, positive, and so on and so forth. Positive, negative, so on. Right? Maybe this will give you the result that you want. Now, hypothetically, if this is the case, then this thing here must be negative, I think, right? And then the sum of 8 will be positive. So okay, let me label it first so that I don't have to keep on referring to it. So if I want them to be true, maybe I can call the positive one P and the negative one N, right? So we can conclude that 3P plus 2N must be less than 0. But at the same time, if I take 8 of them together, I can see that 5P minus 3N must be bigger than 0. So how to choose certain numbers that look like this? Well, maybe I choose this to be negative 1, right? Maybe I choose this to be positive 1. Is that possible? So in that case, we can, for example, add up 3 copies of the first one together with 2 copies of the second one. Okay? Wait, sorry, this is a plus as well. Sorry, because I'm adding the negative terms, right? So I take 3 copies of the first one, 2 copies of the second one, I combine them, then it's possible. 9p plus 6n is negative 3, 10p plus 6n is 2. So then p is supposed to be 5. And if you go and look back at what's n, you will see that n will be negative 8. So it turns out it is possible, right? If you just do 5, negative 8, 5, 5, negative 8, 5, 5, negative 8, 5, 5, negative 8, then the sum of any 5 consecutive numbers will be negative 1. But the sum of any 8 consecutive numbers will be 1, right? Just like how we constructed. So 11 is indeed possible, right? So this idea of thinking for this question makes this feels really like a round 2 type of question. So they put like a round 2 type of question in an MCQ question for round 1, which is really shocking to me when I saw this question just now. Anyway, let's move on. Question 5. Find the sum of all the digits from 1 to, I think this is 10 million. For example, the sum of everything from 23 to 27 is given as follows. The idea is to put what we call padding zeros. Basically, zeros in front of the numbers so that we can add them up easily. If you put padding zeros from 0, 0, 0, 0, 0, 0, 1, I think. Okay. No. I want to maybe one less. Right. Yeah, I do padding from here. 0, 0, 0, 0, 0, 0, 2 all the way up to 9999999. Let's exclude this number first for now. Let's exclude it for now. Then what we can get is the number of 1, 2, 3, 4, 5, 6, all that in 9 is the same. And if I include, let's say, the number 0, 0, 0, 0, 0, 0, 0, then what we can conclude here is that the number of 0, 1, 2, all the way up to 9 are the same. And this is very important. If the numbers of 0, 1, 2, all the way up to 9 are the same, then I can count the number of digits very easily. Right, we can see that there are total of how many numbers? There are a total of 10 to the power of 7 numbers. Right? So each digit will occur 10 to the power of 6 times over here, because they occur with equal frequency. They occur 10 to the power of 6 times over here, they occur 10 to the power of 6 times over here, 10 to the power of 6 times over here, and so on and so forth. So there will be 10 to the power of 6 of each of 0 plus 1 plus 2 plus 3 all the way up to 9. Right. And then we need to add 1 because of the fact that we miss out this guy. So the answer will be 10 to the power of 6. Oh wait, I forgot something. Sorry. I forgot to multiply by 7 because we have 7 columns, right? So actually this will be 10 to the power of 6. Then 45 times 7 actually will give you 315. Oh. Like that. And then we add 1 for the number at behind. So that is the answer. Okay. So they're a little bit tricky, right? Because they offer you part B, which is the case where if you accidentally times 6, you will make a mistake here. But anyway, the correct answer is C. Okay. So far the MCQs, they weren't too bad, except for this a very shocking question number 4. But when I took a look at the level of difficulty of just the first few short answer questions, already I can feel a challenge. Usually, in the SMO, the first few short questions, so questions 6 to question number 10, they are supposed to be not very challenging. But over here, already you can see, oh, they are scary. Question 6 is a recurrence question. They give you this sequence, an minus 2 plus an is 1 plus 2 of an minus 1. The way to do this question is to look at the difference of two numbers in the sequence. Because if we rewrite it to an minus 1 is 1 plus an minus 1 minus an minus 2, then there's something you can notice here. There's something you can notice is that we can set each of these two things as some kind of difference, right? So if you let, for example, bn be the difference between an and an minus 1, then you just get bn is 1 plus, bn minus 1. And now this is a very easy to understand recurrence, right? What do you start off with? You start off with b1 equals to 0 because of the fact that these two things, they differ by 0. So naturally, b2 will be 1, b3 will be 2, all the way. And to find out A26, we are going to use each of these differences. To find out A26, we're going to write A26 as A26 minus A25 plus A25 minus A24 plus A24 minus A23. It's somehow like a telescoping series, right? All the way to A1 minus A0. Of course, at the end, we need to add A0. So what's this? Well, we know that this is the same as B1, same as B2, same as B3, all the way until this is B24, B25, B26. Right, and so the value here will in fact be 1, and then this part here will be a 1 plus 2 plus 3 all the way until plus 25. So it's a 25 times 26 over 2, right? And then the final answer for this question, once you calculate out, is 25 times 13. This is 325 plus 1 is equals to 326. Finish. Okay, next one, question number 7. This question is quite interesting to me because personally, I have actually investigated this question before, a few years before this question actually came out. So I was in my mind, actually, I call this thing illegal fractions. Because why I call this thing illegal fractions? I call this thing illegal fractions because by right, you shouldn't be simplifying 16 over 64 by saying that, oh, I can just cancel out the 6 to get 1 over 4. So of course, that's not the right way to evaluate fractions, but turns out it is possible in these cases. So what's supposedly an illegal way to simplify fractions become the actual way to simplify them. Right? Now, because of the work I've done, I think 3 or 4 years ago, I know the answers because I can remember every single one of them. I know that there are exactly 4 of them. 4 is the answer. And I know that the numbers here are 19 over 95, 16 over 64, 49 over 98, and 26 over 65. This is from my work done many years ago. But from my work done many years ago, I can also determine that this took me roughly 1 hour to find. So a question for which this kind of fractions took me roughly 1 hour to find is a question 7 in the SMO Senior round 1. Let think about it for moments. If you think about it for 4 moments, you'll be thinking, huh? What? How is that possible? So already I can see just by seeing this question number 7 that, oh no, this is a very difficult SMO Senior. Okay, let me show you how to find the number. So the way to find the number is to set up the fractions. Firstly, what kind of fractions can you have? Now, if you cancel out the first digit, it doesn't quite work. If you try to solve, for example, what I mean is that if you try to solve AB over AC equals to B over C, there's no solution. This is quite easy to see because in the end, you can just see that B must be C. Okay. Then the other one, it will be, I think, pretty similar. So if you have A, maybe, okay, let's do it this way, BA over CA. Then if you set this to be B over C, you will get the same result as well, which is that B is equals to C. The one that all four of these satisfies is the one that says AB over BC is equals to A over C, right? After you cancel out the value of B. So then what we can do is that we can write it as 10A plus B, 10B plus C equals to A over C. And then we have 10AC plus BC is 10AB plus AC. Rearrange, we can get, and in fact, I'm going to bring this over to the right because in all of our examples, you know that actually B is bigger than A. Right? So if B is bigger than A, I want to make sure that this guy minus this guy is positive. So I want to get B minus A times of C on the left. And then I want to get 10A times of B minus, we want to get this thing on the left, basically. And we want to get this thing on the right. B is always going to be the biggest digit among the three of them. Now, even here, there's a lot of cases to consider. And because of the lack of time, I'll not run through the entire thing. What do you need to consider? How to start? Well, the right hand side is a multiple of 10. So the way you do this is you discuss where is the multiple of 10 coming from. Can either one of these be 10? No, right? They are single digit numbers. And if they are single digit numbers, basically the main thing is, okay, there's no 10, so there must be a multiple of 5 that's exactly 5. So either B minus A equals to 5 or C equals 5. Of course, when B minus A equals to 5, we need to discuss how to get multiple of 10. C could be 2, 4, 6, or 8. And when C equals to 5, we need to discuss B minus A can be 2, 4, 6, and then 8 as well. So dot, this is where you do a lot of case work. That's where the majority of the time I spend on this question comes from. And then you get these 4 answers in the end. So there's no point for me to run through all these things because it's just casework and it's very extremely tedious, but you can get these 4 answers. Now, when I was investigating this a few years back, actually I found more about this. Just for fun, this is not actually involved in this question. The reason why I stopped at calculating this kind of 2-digit cases is because for 3-digit cases and so on, it is automatically true. For example, it is automatically true that 199 over 995 is 1 over 5. In fact, it's true that 1999 over 9995 is equals to 1 over 5. It is true that 166 over 664 is equals to 1 over 4. It's true that 499999 over 99998 is equals to 4 over 8. And of course, it doesn't matter how many 6 you actually put inside here, as long as it's the same number on the top or the bottom. So it doesn't matter how many of this extra digit B you put. Turns out, they will always be true. Right? So by finding the 2-digit cases, basically you are finding the 3-digit cases and so on and so forth as well. Okay? Although technically it may not cover every single thing, right? Because technically there could be a case where what? There could be a case where you have something like ABC over BCD is equals A over D. Okay? If any of you are interested to explore that case, you can go and give it a try, but I recommend don't do it because already the 2-digit case took us such a long time, right? It's probably not worth calculating the 3-digit case. Okay, let's continue on. Next question, question number 8. Just by looking at the question alone, you should already feel that, oh, this question is a little bit sus. What do you mean by little bit sus? Okay, these things we know they probably are related to difference of squares. Right? But somehow when I multiply them, I can't seem to use it. Right? We know for a fact that a plus square root of a squared plus 9. I'm going to rearrange that term in fact. I'm going to write the other guy like this. Must be what? This must be the value of 9, right? And I know that b plus square root of b squared plus 1. And then let me rewrite the other term like this. It must be 1. This is pretty obvious difference of squares identity. But how is it related to this? And notice the right hand side is 3, which is somehow like the square root of 9, which may be important. So they are probably related to each other in some way. So at first I thought about multiplying them together. So if I know that this product is 3, then this product is 3 as well. But that doesn't tell you much. Right? That doesn't tell much. So here's the idea. The idea is that you already know what A is. Okay, so let's bring that thing over. So we can write it as b plus square root of b squared plus 1 is 3 over this. Now a is very big. A is what? A is 2026. So naturally, this is a value that's very small between 0 and 1. So is b positive or negative? Well, b cannot be positive then. B must be negative, right? This guy will become more positive than however negative b is. So therefore, the result will become a very small positive number. Okay, so if I write it on the right hand side, I can use this fact and rewrite it as square root of a squared plus 9 minus a over 3. And at this point, there may be something you can notice already. B is supposed to be negative, A is supposed to be positive, but here you have a negative A. Okay? So it's already of the form something subtract something. This is already on the form something subtract something, right? Because technically B is negative. So what can you do here? You can use the fact that there's a square root 9 and there's a 3 here. Rewrite it as minus A over 3 behind, but in front I can bring the divide by 3 in, so that I have A over 3 squared plus 1. Suddenly, if you compare both sides of this equation, you can already see B is simply just negative A over 3. Okay? This is a very important conclusion from here. And then from here, we are done. B is negative A over 3. B will be equals to negative 2026 over 3. So when you round down the value of B, it will be negative 676, I think. Yeah, so the answer should be 676. Okay, one remark about this is that, okay, we don't really care about this because it's SMO round 1, right? But one remark is that how do you know, let's say you're doing logical reasoning, how do you know for sure that this will guarantee you B must be this negative A over 3? The way you can think about this is that you can argue it as a function. Right? This function here of square root of x squared plus 1 minus square root x. Sorry. This function here is actually monotone. What does it mean by monotone? When x equals 0, this is the biggest. And then when x is positive, it just decreases all the way. Right. So if this is a monotone function, the only way that a function, the value can match a monotone function's value is when it's equal to itself. For example, for monotone function fx, if you know that fx is equals to fy, then x is equals to y. Right? This is a property, what we call injectivity. You may have heard of this before. Okay, anyway, let's move on to the next question. Question number 9. This is a scary looking expression. Let pi be xi to the power of something. Now here notice that you have ln of x1, ln of x2 all the way, but you don't have ln of xi. So for xi itself, the power here is gone. Now immediately when I'm taking a look at this, my first step is to think, okay, this power is so big, is there any way I could take the power down? Turns out there is. Whenever you have logarithms, okay, so let me use some logarithms to illustrate this fact. Whenever you have logarithm of something to the power, you can always drag the power down in front. So that helps you to bring down powers when you use logarithms. So when I take a look at the first expression, immediately I'm thinking, okay, maybe I should put ln on both sides. Okay? Maybe I should put ln on both sides. In fact, let's test the theory out. What happens if you put ln on both sides? If you put ln on both sides, you get the ln of pi is equals to what? Ln of this guy, right? But the power is this. We can bring down the power, put it in front. So there's a ln of xi at back, but then there's a ln of x1, ln of x2, the ln of xi minus 1, ln of xi plus 1, the ln of x100. Really many terms. Huh? But if you notice something, hey, this ln of xi is exactly the missing term we have over here. It is exactly the missing term we have over here, right? So what does it mean? So it means that exactly this is the product of all the lns, right? Where k goes from 1 to 100. Right? In fact, every single thing is here. This is exactly the expression that we're looking for. And since this is independent of the value of I, it means that ln of pi is the same. P1, P2, P3, and P100, they are all the same as each other. So that means that this guy here is actually exactly 100 times of P1, for example, right? Each of them are the same. So P1 is going to be 100. The answer for this question is going to be ln of P1, which is going to be ln of 100. Now, of course, you still need to do ln of 100 round down. The main thing here is to think. Ln of 100, okay, it's basically base e, right? Is e to the power of 4 and e to the power of 5. Okay, actually, no, e to the power of 4 is obvious. E to the power of 4 is obvious because, wait, is e to the power of 4 obvious? Not necessarily. But for example, you can see that, okay, e to the power of 4 is roughly going to be 2.718, right, to the power of 4. Here, 2.7 squared is obviously less than 8, right? So it's less than 8 squared, right? So this is going to be less than 64. So e to the power of 4 will obviously be less than 100, right? But then what about e to the power of 5, for example? E to the power of 5, again, you can think of it as 2.71 e to the power of 4. Now here's the thing, 2.7 squared is 7.29, so it's bigger than 7. Oh, sorry, this is power 5. It's bigger than 7.29 squared times 2.71, right? So it's bigger than 49 times 2.7. So it's bigger than 100. So now we know for sure that your 100 is between e to the power of 4 and e to the power of 5. So this is going to be between 4 and 5. Okay. Finish. Okay, next. Somehow, after doing these very weird questions, right, a lot of different type of questions, somehow we seem to get to question number 10, which is like a primary school math Olympiad kind of question. Right, we have x degrees be the angle between the hour and the minute hand when the time is 3:15 p.m. Find the value of 10x. So if you're hoping to get around 2, this is the question you must score on. If you don't do it, then it's quite shameful. Not quite shameful. No, that's not the right word. It's quite a waste. Not shameful. Sorry, that's not what I meant. It's quite a waste if you didn't manage to do this question. Huh? So wait, why am I drawing this? Sorry, the hour and minute hand is 3:15. So we know that the hour, or rather the minute, will point exactly at 3. The hour will be somewhere between 3 and 4, right? But where is it? So I'm going to draw a dotted line to the number 4. And we can see that the hour hand should be here in between, right? And since it's exactly 15 minutes past the 15 minutes past the hour, it should be 1/4 of the way. So if I compare them, that means I'm going to split into 1 unit and 3 units. So it's easy to tell that this is a 30-degree angle as well, because of the fact that there are 12 hours in the clock, right? So 30 degrees, I divide it into this, what I get? I get 7.5 degrees, right? And something else. But either way, it tells us that, oh, the angle over here is going to be 7.5, so naturally 10x will be 75. Okay, this one is pretty straightforward. Continue. Here, question number 11. This is a question which I'm quite surprised that they included here, because this question uses a fact that I somehow can remember, but I've forgotten the name of this fact. That's the thing. I just remember it as some kind of theorem. If I forget the name of a particular theorem, that means it's pretty obscure. So here is an obscure fact. In a circle, if you have 2 perpendicular diagonals, like this here, you draw 2 of the sides. Okay, maybe I try not to make it too symmetric, because that one is not good for observation. Maybe I try to make it as non-symmetric as I can. Huh? Okay, I connect 2 of the sides like that together. Okay, if I take the midpoint over here, I draw it through the common point, then the fact is that it'll be a right angle on the other side. Okay, so the obscure fact is this. Here, basically have A, B, C, D. Okay, let's follow the notation in the question. A, B, C, D like this, right? If you have AC perpendicular to BD, And then if you have M is the midpoint, right? And then MEN is going to be perpendicular to AD. This is the fact. Now, firstly, it is basically what this question wants. Because in this question, this is a right angle. They tell you because they tell you AB is a diameter of a circle that passes through AB and E. Right? So imagine that this is the diameter of a circle passing through AB and E. That means that angle E is going to be a right angle, right? Okay. So here M is the midpoint. Now, how to show this obscure fact is that we can use angle chasing. So let's say we start off with this angle. Let's call it angle X. Okay, maybe let's not call it X because this question has X. Let's call it angle Y. This is angle Y as well. This is angle Y, right? But because of the fact that angle BCA is equals to angle BDA, this thing here will also be Y. So the thing beside here will be 90 degrees minus Y because of the fact that this is a right angle, right? Angle AD is a right angle. So therefore, if it's 90 degrees here, then it will also be 90 degrees here. So that's the proof. And that means that we're done. Because using this obscure fact, BC is 28, so tells us that 14, 14, ME is naturally 14, but AN is 27 and ND is 3. And when you have such a fact, which is of the form of a right angle triangle with a right angle with an altitude here, a more well-known fact is that xz equals to y squared. That's due to similar triangles. Similar triangles where you have x over y is equals to the ratio of y over z. So immediately you can figure out that this is 9. So Mn is going to be 23. So maybe that's the reason why this obscure fact doesn't really have a name, because it's quite easy to show, right? Turns out I just need to do a bit of angle chasing to show it. Okay, let's move on. Here, let there be 6 real numbers such that the product of the tangents is equals to 1. Let A be the maximum value of the sines, determine the value of A inverse round down. So if you're doing this during SMO itself, naturally you will think that the best way is when all the values of x are equal to each other, right? So naturally you should think that, oh, if x1 equals to x2 equals to equals to x6 equals to 1 equals to pi over 4, right? Because their tangents will all be equals to 1. Then it feels like this will give you the maximum value. A will be 1 over square root 2 to the power of 6. So A will be 1 over 8. So then the answer here will be 8. But that is just intuition. Because intuition anyone can do. Right? But since we are doing this seriously, let's do it as kind of like a round 2 kind of idea. Right? Round 2 kind of idea. Why must the maximum value of A be 8? Actually not maximum value, sorry. Maximum value of A is 1 over 8. That's what I mean. Why is it true? Well, the idea is that we can do a smoothing-like argument. So basically, we're talking about round 2 arguments at this point. If you don't care, you can just don't listen to this. But I think it's a nice, interesting way of thinking. Fix x3, x4, x5, x6. We will just play around with x1, x2. Right? So suppose that tangent x1 times tangent x2 is fixed. Why is that fixed? Actually, we don't need to suppose it. The supposed to be in the first line. Because if suppose we fix x3, x4, x5, x6, then this is fixed, this one is fixed, so naturally this product is also fixed. Now you can think about, okay, if these 4 are fixed, how can we maximize the product of x1, sine x1 times sine x2? I will show you that in fact it's when x1 equals x2. Right. So the way to understand this is, okay, let me draw out the following diagram. Tangent of x1. So let's say that this is x1, this is 1. That's the angle we're looking for. Tangent of x2 is something similar. Then how do I know what sine x1 times sine x2? Well, the hypotenuse, we know what they look like, right? By Pythagoras theorem. So in fact, this is x1 over this guy, x2 over this guy. So if you now write it out, it's x1 times x2 over Oh wait, I just realized my solution is wrong because it's not x1 times x2 is fixed. Okay, so let me mention what I was trying to do. What I was trying to do is that I was trying to do this. I was trying to do this and then see that because x1 times x2 is fixed, this is fixed, and I want to basically minimize this. So that's why I want to let x1 equals x2. But now I realize x1 times x2 is not fixed, right? Yeah, it's this that's fixed. Okay, that is a little bit weirder now. This is a little bit weirder. Yeah, how do I do this now? Wait, I just realized tangent of x1 is not even the one that I described. I'm talking about tangent in wait, what am I talking about? Wait, I just realized. Wait a minute. My diagram is completely wrong. So my diagram is completely wrong. Okay. My diagram still can be salvaged. Basically, what I'm saying is that x1 is supposed to be an angle. So for example, x1 is this angle here. What am I doing? Okay, x2 is this angle here. So tangent of x1, let's call it A. Okay, tangent x2, let's call it B. Then I don't need to change much. I just need to change this A and B. Like that. Right. So in fact, I don't need to change most of these expressions. Just replace them with A and B. Okay. So if tangent of x1 times tangent of x2 is fixed, is that AB is fixed, not x1 times x2 is fixed. So that's why I made a mistake just now. But either way, the argument still holds. Okay. If A times B is fixed, then this thing here is going to be maximized when? It's maximized when your A squared plus B squared is minimized. Right? Because this is fixed, so only cares about this term. So when is this minimized? Of course, by AMG inequality is when A is equals to B, right? So therefore, if this is fixed, we actually want x1 to be equals to x2. And so now we understand, okay, it's better to, instead of x1 and x2, just replace them with x1 plus x2 over 2 and x1 plus x2 over 2. And as a result, the value of the function, the value of the expression A will increase. So by doing this, eventually you can see that the maximum value will occur when what? All the x1, x2, or so on and so forth are going to be the same. So that's the proof you can write down if they, let's say they ask you why this is true. Okay, but intuitively, you should already arrive at this step very easily, right? Okay, anyway, let's continue on to the next question. Question number 13. This is a relatively standard kind of idea. In fact, we did something like this back then in Sec 2 semester 1 lesson number 15. Cannot remember. It's been a while. Okay, so we have exactly that question. I remember that question back then was f 2016 plus f0 minus 2016 factorial. So this is a very similar kind of idea. So you have a polynomial. A64 equals 1 tells you that it's in fact monic. So the highest power term is just x power 64. Now they tell you that p of j is 10 times j for j equals to 1 to 63. Your first instinct on considering this should immediately be to construct a function, a polynomial qx to be p of x minus 10x. So this will be what? This will be 0 now when x equals to 1, 2, 3, or 63. Right? So this thing here will be 0, is 0 when x equals to 1, 2, 63. So naturally there will be factors x minus 1, x minus 2, x minus 3, all the way until x minus 63. But you cannot stop here because originally the polynomial p is a degree 64 polynomial. Right now you have a degree 63 expression. So you still need to modify it by multiplying by a certain x minus a, or maybe let's call it c, some constant c. And now you are done because right now you have a degree 64 expression. And you can check that it must be x minus c and not anything else like k times of x minus c, because it is monic, right? The A64 term is 1. Okay, now what you can do is that you can just put in 66 and negative 2 inside the expression. So what happens if you take Q of 66? So if you take Q of 66, you have 66 minus 1, 66 minus 2, all the way to 66 minus 63. So that's going to be 65 factorial over 2, right? Because the only thing missing is 2 times 2 times 1 from the 65 factorial. But then when you put 66 inside here, this will be a 66 minus C. Okay, then Q of negative 2 will be equals to what? When you put x equals negative 2 here, you get negative 3. When you put x equals negative 2 here, you get negative 4. Or then here you get negative 65. So you get a negative 65 factorial over 2, right? Because it's missing the negative 2 term and the negative 1 term. And when you put in x equals negative 2 here, you can get negative 2 minus c. So in fact, this is 65 factorial over 2 times 2 plus c. So when you sum them up, you know that this is 65 factorial over 2 times 68. Okay. So now what you want to do is that you want to figure out something. You want to figure out, firstly, what this is in terms of p. What this is in terms of p, when you figure it out, is that you are adding these two expressions together, right? For p66 and p of negative 2. So together, this is p of 66 plus p of negative 2 plus minus 640. So this guy is the same as this guy. Okay, so we can figure out that p of 66 plus p of negative 2 is equals to 640 plus this guy. And finally, we need to find our remainder when divided by our favorite number. So here what we can do is that we can use Wilson's theorem. So Wilson's theorem says this thing. It says that for prime numbers p minus 1 factorial is congruent to negative 1 mod p. Now immediately, this tells you something. Immediate consequence of Wilson's theorem is that as long as p is not equals to 3, wait, no. It even works for p equals 3. So as long as p is not equals to 2, wait, no, it also works for 2. But basically what I'm trying to say is that p minus 2 factorial is congruent to 1 mod p. The reason is because of the fact that I'm just dividing by p minus 1 on both sides, right? So this is equivalent to saying Wilson's theorem. Right, this is an equivalent statement. So when you put it to p equals to 67, right, then 65 factorial will be immediately remainder 1. Yeah. Okay. So this is what we have. Now, 640, you can think of it as negative 30, because 670 is a multiple of 67, right? So together, this is 4 mod 67. Finish. Okay, question number 14. This question here, the part on top reminds you specifically of, I forgot which one it was again. Also Sec 2, also semester 1, but it's lesson 16, I think. Yeah, because I just taught it a few weeks ago, so I kind of remember this. Back then, what the question was this was a question from the SMO open section in the year 2012, maybe. What the question wanted to find is basically find the maximum of these three terms. And turns out those in that question, they were 8, 4, and 2. So it's possible to solve for the values of alpha, beta, gamma. In this question though, it's not possible to solve. Because in the end, when you get a cubic, it's not a nice answer. But you don't need to solve. The cubic itself helps you to find this. Okay, I'll talk about how when we get there. First, we find the cubic with the solutions being alpha, beta, gamma. So immediately, you can see that this is something we can calculate, because this is half of the sum of squares minus away like that, right? So this is 9 minus 5 divided by 2. And immediately, you can also calculate alpha, beta, gamma. And the way I calculate it is to use this equation. this formula. Okay, hopefully you still know this formula because we definitely mentioned this before at some point. Okay, so we just put in the values here. We can see that this is going to be 12, 3, 5 minus 2, right? So this is 9 on the right side. So definitely it should be 12 minus 3 times of 1, right? Okay, so we know that alpha, beta, gamma is equals to 1. So after figuring out this and figuring out this, what you can do is that you can form the cubic equation. So if you consider this certain cubic equation, x cubed minus away 3x squared from here, plus 2x from here, and then minus 1 from here equals 0. This thing here has solutions alpha, beta, gamma using Vitas theorem. Okay, this is by Vitas. Okay, and after finding the cubic equation, now how to continue to figure out the sum of power 5s? If you know Newton's sums, you are welcome to use it. So here's a note for you. Read Newton's sums. But if you don't remember Newton's sums like me, because I can never really be bothered with it, I think the amount of question it can be applied to is very, very small. Then you can get punished because you don't know about Newton's sum. But either way, it's possible to find out this. How come? Because, for example, alpha is a solution of this. Means that alpha cubed minus 3 alpha squared plus 2 alpha minus 1 is 0, right? So alpha cubed is equals to 3 alpha squared minus 2 alpha plus 1. I can do this a reduction of powers. So I can reduce alpha to the power 5. Okay. So from here we can say x power 5. Okay, so let me rearrange this. X power 5, I can think of it like this. I can think of it as x times x power 4. But x power 4, I convert it into, sorry. No, I want to think of it as x squared times x cubed. And x cubed is this guy. Okay, so this is 3x power 4 minus 2x cubed plus x squared. And I do it again here. I write it as 3x times x cubed, which is this guy. Oh, sorry, I forgot the behind terms. So when you do simplify this expression here, what you can get is 9x cubed minus 2x cubed, so it's a 7x cubed, minus 6x squared plus x squared, so it's a minus 5x squared, and then this is a plus 3x. So if this is true, then immediately you can figure out something. You can figure out alpha 5 plus beta 5 plus gamma 5 is 7 alpha cube plus beta cube plus gamma cube minus 5 alpha squared plus beta squared plus gamma squared plus 3 alpha plus beta plus gamma. It's just this same equation being reused 3 times. One for alpha, one for beta, one for gamma. And then now we can add them together. Okay. So then now we can calculate out 7 times 12 is equals to 84 minus 5 times 5, that's 25 plus 3 times of 3, answer is 68. Okay, next question. Question number 15. I'm very happy that this question came up because I just finished going through this question with my Sec 3 class a few weeks ago. Once you see that the angle double, already you should already see what's going on. Right, in case any of my Sec 3 students are currently watching and don't remember which question this is the same question we did last time where we saw the cosine 36 degrees times cosine 72 degrees. It's the same thing we did last time when we saw the cosine 12 degrees, cosine 24 degrees, cosine 48 degrees, and then cosine of 84 degrees. Is these two questions. How did we do these two questions last time? We did these two questions by multiplying by sine 36 degrees to apply double angle formula for the first one. We did the second question by multiplying by sine 12 degrees to apply double angle formula. Same thing for this question. Firstly, this question is 1 over this. And at this point, I think you should know what to do. we're going to multiply our cosine 2 pi over 9, right? Cosine 4 pi over 9, and then cosine 8 pi over 9 by the value of sine 2 pi over 9. So this one here will be half of sine 4 pi over 9. Then this one here, when you multiply, will be 1 over 4 sine of 8 pi over 9. And this one here, when you multiply, will be 1 over 8 sine of 16 pi over 9. But the magic thing is that these two guys are the same. These two guys are the same because of the fact that 2 pi over 9 and 16 pi over 9, they add up to a value of wait a minute. Oh, it's slightly different than last time. Yeah, because last time we deal with angles within 180 degrees. But here, if you add them up, you get 2 pi, right? We get 360 degrees. So these two are not quite the same thing, but they are negative of each other. So because of the fact that 2 pi over 9 plus 16 pi over 9, this is equals to 2 pi, you can see that sine of 2 pi over 9 will be the negative of sine of 16 pi over 9. Okay. Oh, sorry, I meant to write it down fully. Okay, let me just write down the conclusion. Okay, so from that, what you can see is that, these two things are just going to be a negative of each other. Therefore, the value of A, or rather, not the value of A. Therefore, the product here will be negative 1 over 8. Therefore, A itself will be negative 8. So the answer is 8. Okay, next question. Let's draw the diagram. So circle has this equation. Okay, so it's centered at 10 and 10 square root of 3. So if you draw out the coordinates, you should already know basically where this point is, right? So 10 and 10 square root of 3 is part of your 30, 60, 90 triangle. So perhaps you can draw it like somewhere here, right? Somewhere like this point. And then the radius of this circle is the square root of 39. Square root of 39 is roughly going to be between 6 and 7. So the size of this circle probably will be somewhere like here. Okay, maybe a bit bigger. But either way, what does the question want? I want a line L tangent to C, passing through the origin. There's only two such line Ls that work. Either this or this. They are tangent to the circle, right? And I want that to happen where A is the largest real number with this point AB. So means what? Means that the x coordinate is as large as possible. So out of these two points of tangency, which point has the largest x coordinate? You can see that it is the line below. So it's the line below. Let's draw that in. This is the tangency line we're looking for. Now, I want to find out this coordinate basically because the question wants us to calculate b over a as the value. And it looks a bit scary, right? There are two ways to do this question. The first way is to use coordinates. So more coordinate account method. Okay, but before that, for both solutions, there's something that you must do. You must draw out the radius. Right? It's not hard to see that this radius here will be equals to 20, right? Because of the 10 and 10 square root of 3. And if you take a look at this thing here, it's square root of 39. So immediately, you can see that the length of this one should be 19 because of the fact of Pythagoras theorem. So the length here is actually an integer. Okay, so you can try to go and figure out what this value is, right? And it shouldn't be too bad because wait, now I'm thinking, is it possible to use similar triangles? No, not quite possible to use similar triangles, no. Okay, so I was thinking maybe it's possible to draw this one and then this triangle is similar to the everything else, but this triangle will not be similar to the current shape. Right? It will not be similar because we don't know anything about this angle. This angle is the same as this angle, right? These angles are same, but which is not related to this angle. So there's no kind of like similar triangle you can do for this. How do you do this then? Well, one thing that you do know is that this is a 60-degree angle, right? We know this is a 60-degree angle because of the fact that this is a 30, 60, 90. So let's try to use it. Oh, sorry, I forgot to talk about method number one. My method number one is this. Method number one is to use algebra. So I won't be using this. So I'll just mention it quickly so that you can consider it. Huh? So you can set your A and B so that this distance you do know, right? You do know the distance here. And then you know, what else do you know? You know that this is 19. Right? So you can set up equation, you know what this is, you know what this is. In fact, you can use the fact that they are perpendicular. You can use the fact that they're perpendicular and you know the fact that, for example, this is 19. So one thing is that a squared plus b squared is 19 squared. You also know that this is perpendicular. So the radius here and the radius here, sorry, radius. The gradient product is -1. Right? So this is one idea. But this is not the method I will use. The method I will use is to depend on angles. Now for this one, there's a very special thing that you can read up on. I will not bother to explain this. So read on rotation matrix. So if any of you are interested or have learned about matrices, there's a certain type of matrix that can do rotation and it will do it pretty effectively. It will help you calculate things very quickly. But if you want to don't use this one, also can. The idea is that you can label the two angles. For example, this is angle, let's call it theta 1. This is angle theta 2. What I want to find, B over A actually, if you think about it, is this over this. B over A is the tangent of theta 2. So the trick is that we're going to use the fact that their sum is 60 by writing tangent of 60 degrees minus theta 1. Oh, sorry, I haven't simplified it yet. So let's write it like this. And then we can use our tangent difference of angles formula. And the good thing is that I know the value of tangent of theta 1, right? Based on the diagram. Okay, firstly, tangent of 60 degrees is square root 3 over 2. Wait, no, that's not correct. Sorry. Tangent of 60 degrees is square root 3. Based on the diagram, tangent of theta 1 is what? Is square root 39 over 19. So that's where you can already see these numbers come from, right? Okay. It's a bit ugly here, but you can simplify it. So for example, one thing I like to do here is multiply both the top and bottom by 19. And then you get some very ugly expression here. Square root 117, in fact. And then now we rationalize it. Right? Quite a common idea. Denominator will be 361 minus away 117. This is actually 244. Numerator here will be so this guy times this guy is 361 square root 3. This guy times this guy is square root 13 times square root 3. And then what's this? Wait, I'm a little bit confused. Wait, what happens when multiply? Okay, square root 13 times square root 3, square root 13 times square root 9. So it's basically 13 times 9, which is 117 once again. Wait, what? No, sorry, 13 times 3, so it's 39 square root 3. Okay, a little bit confusing. Then this guy and this guy. But basically you get the point. Right? So the other one, I'll just write it down for you. There will be a minus 19 square root 39 from here. There will be a minus, what's that actually? Minus 50 something, right? I remember. Minus 57 square root 39. So together it looks like this. Okay, so basically, once you get here, then you realize, this is basically what my answer is. My value of alpha is this guy. My value of beta is this guy. Right. So in fact, you don't have to care about the 244 because alpha over beta is just going to be 400 over negative 76. But it's negative. So when you round down, it becomes what? it becomes -6 instead of -5. And so when you take absolute value, 6. Okay. Okay, that was a little bit of a long-winded question, right? Pretty tedious. Okay, let's continue on. Question number 17. In the diagram below, we have two circles, centered at O1, O2. They have two common external tangents. In fact, three common external tangents, but this is a right angle. Right. So immediately, when I'm looking at this diagram and seeing that PQ equals 11, I'm tempted to draw out something. Tempted to draw O1P and O2Q. And not just I'm tempted to draw out these two lines, I'm tempted to draw out more. I'm tempted to draw out O1C and O2D. I can get two squares, right? Now, they tell me that PQ is 11. Okay, that's very nice. O1, O2 is 61. How to use these two facts? In fact, we can find out the bottom length. Because if I know that this is equals to 61, and the 11 I can actually bring right here. I can bring it right here, 11, right? So then the bottom length is square root 61 squared minus 11 squared. If you calculate that out, you can get 60. So this is the length at the bottom. 60. Now we can attempt to find EF by using the fact that we have some common tangents here. So this is 60, immediately tells you that this is 60 as well, because the lengths of the two tangents, they are equal, right? Always true for these two circles. So I can label maybe the two lengths on top as A as B. So EA as A, EB as B. Then EP equals to A. EQ equals to B, right? Because of the common tangents. Okay. Now, what about PF? PF here is equals to the same radius of the small circle, right? Let's call it R1. And then QF is the radius of the big circle. Let's call it R2. But in fact, we know what R1 plus R2 is. We know that R1 plus R2 is basically just CF plus FD, right? Because this is a square, this is a square. R1 plus R2 is 60. But also, A plus B is also 60. So what do we know about this? This must be 60 as well, because EF is equals to A plus R1, but it's also equals to B plus R2. So in fact, if you know R1 plus R2 is 60, A plus B is also 60, then together this is just 60, 120 divided by 2. So EF is also 60. Finish. That's the answer. So we know from here, actually, the letter A must be R2 and the letter B must be R1, which is pretty interesting. Okay, finally, the easiest question on the worksheet. Okay, maybe not the easiest. Okay, probably the easiest question on the worksheet. X cubed minus y, x cubed plus y equals to 7. So this has to be 1 times 7. This is 1, this has to be 7. Right, because y is non-negative. So if you solve for them, 2x cubed is equals to 8. X cubed is 4. Answer 0. Okay. I don't know why they put this question in the middle of here. I think that should be the original question, right? But it looks a little bit funny. And the answer is 0. Okay. Question number 19. This, once again, is a pretty famous question. There was a year which I cannot remember which year it was. Forget already. Basically, there was a year which they had a certain degree 5 polynomial. Then they say, okay, you have a x power 5 minus away 20x power 4 plus bx cubed, and if all the roots are real numbers, find something involving b. So as you know, 20 is the sum of the roots. B here is the sum of the pairwise product of roots. So it's very similar to this question. How do we deal with this? Just like for that question which we did last time, we're going to introduce this a1 plus a2 plus a3 plus all until a something squared. And the way to introduce this is that we need to make sure that, okay, the sum of squares can appear on the right hand side as well. So we're going to artificially introduce this. We're going to add, we're going to multiply by 2 first to make our life easier. So we're going to multiply by 2 and then put a 2 here. And then we're going to add KAI squared, the summation of it. So it means I'm going to add K of A1 squared, K of A2 squared, or K of AI squared to both sides. But then the right hand side becomes very nice because the right hand side becomes now K times of what? K times of, you have the sum of AI squared, but you also have the sum of 2 times of the pairwise product. So we know what that is. We know that this is just K times of A1 plus A2 plus all until A 2026 squared. Right? This is true. Okay. And then on the left hand side, by adding this thing here, I've created K plus 2, right? But now here's a fact about these two numbers. There's this thing that we can use called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality says this thing. It says that if I have n times of a1 plus all until an squared. Actually, okay, let me state the full form first. Let me state the full form and then I'll state the simplified form. So the full form tells you a1 squared plus a2 squared plus all into an squared times b1 squared plus b2 squared plus all until bn squared is at least a1 b1 plus a2 b2 plus all until an bn squared. So here, if you just take, for example, okay, let me write the conclusion here. For example, if you take b1 equals to b2 equals to bn equals to 1, you can just get that. And also, I want to take n to be 2026. And then what I have is just 2026 of the sum of squares will be at least the square of the sum. This is what we have. And this is from your Cauchy-Schwarz inequality. So from here, if you compare, right, what do we have? Basically, the k plus 2 over k is going to be the 2026. Right? The largest of value of k you can choose is when k plus 2 over k is the 2026. Because if you choose something that's even larger, if you choose some value of k that's even larger, this fraction is actually going to get even smaller. Right? This fraction is going to get even smaller, and then at that point of time, you no longer have this to be true because that disobeys the Cauchy-Schwarz inequality. So how to find the value of k? You can see that 1 plus 2 over k is 2026. So 2 over k is 2025. 1 over k is 2025 over 2. Absolute value round down will be 1012. Yeah, I think that's correct. Okay. Let's continue. I really want to pee, by the way, but let me, I guess, finish the entire worksheet first before I go. And question number 20. When I saw this question, my first reaction was like, what the is going on, right? That's naturally everyone's reaction. But I think there's one thing that at least I was a bit happy to see. At least I was happy to see that this is 108A, this is 108B, 108C. So at least I know that's the same. So one thing I immediately did on the right hand side was I separated into 108A plus B plus C, and then there's a 1024 ABC, right? So immediately when I do with this denominator, what's going to happen? In fact, the denominator looks like this, right? So this will cancel out. Okay. And then this one here, the ABC will cancel out. Right. So it's 1024 over A plus B plus C. Now already at this point, I'm thinking of, okay, maybe I can apply some kind of AMGM inequality. Right. How do I apply AMGM inequality? So maybe there's something over here I can get some number of A, some number of B, some number of C, and I have some number or divide by A, B, C. I can apply AMGM inequality to these these four terms, and get rid of the A, B, and C, right? But then maybe there's also going to be some leftover terms of A plus B plus C, and then I can do AMGM on this term to get rid of the A plus B plus C. So in my mind, I already have come up with this. But the question is, I don't know how many of each I need. That's the problem, right? I don't know how many of each. Now, it seems like all the numbers are between 4 and 5. So maybe I can take out exactly 4 copies of A plus B plus C, right? Maybe by that point of time, whatever's left over could be the one thing to deal with it. Now, if I take out 4 copies of A plus B plus C, it doesn't work, then what do I try next? I try to take out 3 copies of A plus B plus C. I try to take out 2 copies. And at the worst, I try to take out 1 copy if it still doesn't work by then. Okay? But let's give it a try. Let's take out 4 copies at first. So this guy here, you have a 4A, 4B, and 4C. I can take out 4 copies. Then this guy minus away 408. Sorry, not 408. 4 times of 108 is 432. So this guy minus 432 is 36. Oh, I didn't mean to write equal. 36A over 108. And then this minus 432 is 27B over 108. And then this minus 432 is going to be 12. Now, when I see these numbers, I'm very happy. Because just nice, 36, 27, and 12 are all factors of 108, right? And if they're all factors of 108, maybe there's already a way for us to cancel out with this guy. Right? Maybe there is a way. In fact, the good thing is that not just they are factors of 108, the 3 of them multiplied together is in fact 108 squared. Okay, it's a little bit hard to see, but 12 is equals to 4 times 3, right? 4 and 36 is 108. No, sorry. 4 and 27 is 108. 3 and 36 is 108, right? So when I see this, I'm pretty happy. I know that pretty much I should definitely have the exact numbers already. So what can I do here? I can do here by doing these 4 terms together. By AMGM inequality, this is at least 4 times of their product. So 36A over 108 times 27B over 108 times 12C over 108 times 108 over A times B times C. And in fact, what's this? This is just equal to, I think it's just nice 4, right? Yeah, because everything inside actually simplifies. Right, all the ABC will cancel out. All the 108 will cancel out as well. And now for the term at the start and the end, again, we can do AMGM on this, right? We can do AMGM, so that's, we can combine the ABC together. So we apply AMGM here on 2 terms now. And what do you get in the end? This is, I cannot math. What's this? 4096 take square root. I think it's 36, right? Yeah. Like that. Okay. So wait, apparently I did calculation somewhere wrong. Let me just check my working. Oh, sorry. Square root of 4096 is not 36. Where did 36 come from? This is a power of 2, right? There's no way you can get 36. Sorry, I don't know what I was thinking. Square root of 4096 is 64. Okay, I don't know where 36 came from. Sorry. 64 then times 2 is 128. My bad. Okay, and now this is correct. So 132. Now, of course, if you're doing this during round 2, you need to do some extra checking. You need to check that the equality can happen. So when does equality happen for AMGM is when all of them are equal. So if the first one, when all of them are equal, what do you get? If the first one, all of them are equal, then basically A to B is 3 to 4. A to C is 1 to 3. So the first one will tell you that, okay, I think, yeah, A to B is 3 to 4, A to C is 1 to 3, so like that, 3, 4, 9. But if it's 3, 4, 9, it's in fact perfect because this is just 1. This is in fact just 1 as well because it's 108 over over what's that thing called? Over uh what's the thing called again? 108 over 12, right? No, 100 over 8, 108 itself. So it's 1. Yeah, so all of them are equal. And let's check, it also works here. If this is the value, you can see the sum is 16. This will be 64. This is 1024 divided by 16 as well. So that's 64 as well. So these two are equal. So you can see they chose the numbers very specially for this specific reason, right? It might look like these are just random numbers, but these are in fact numbers that have been specially chosen so that it can satisfy both of the inequalities at the same time, with A being 3, B being C, and C being 9. Okay. I still have 5 questions before I can go and pee. Question number 21. Let mx be this unique monic polynomial with degree 67, with rational coefficients such that this number is one of its roots. Let A denote the coefficient of x squared. Find the value of absolute value A round down. First thing first is that the numerator looks like a geometric series, right? So that's the first thing you can notice. Okay. If I let the common ratio R be 67 to the power of 1 over 67, then the numerator is pretty nice. Numerator is 1 plus R squared plus R into R to the power of 66. Using formula for geometric series, this is R to the power of 67 minus 1 over R minus 1. Oh, wait a minute. Isn't R minus 1 exactly, isn't R to the power of 67 just 67 itself? You see that yes, right? So this is this value. So when you take this thing, divide by this, it becomes a nice number. So the expression, or rather the root, is equals to 1 over R minus 1. Now, here's the hard part of the question. How do you come up with a polynomial with the root being 1 over R minus 1, where R is this guy? Well, so I want, let's say, x equals to 1 over R minus 1 as a root of this, right? Can we come up with such an equation involving x? Now, the answer is yes, because a few years ago in SMO Junior, there was this question. X equals to cube root of 4 plus cube root of 2 plus 1, find something like 1 plus 1 over x to the power of 3 or something like that. Back then we did the same thing. So here we just need to do something. We just need to make R the subject. Because if you make R as the subject, then what happens is that you can take R to the power of something and make it a whole number. Right? In this case, you can take R to the power of 67, it'll be a nice number. Right? So let's make R as the subject now. R minus 1 equals to 1 over x. You can switch them. So R is 1 over 1 plus x. Then it really looks like that question from the SMO Junior, right, back then. Anyway, now what do? You take to the power of 67, right? Since I said I was going to do it, now I'm going to do it. And here the trick is that I can form a polynomial now. That is a polynomial that works. I can bring the denominator over. The x power 67 part, I can bring it over. I can get 67 x power 67 is equals to x plus 1 to the power 67. So this is exactly the polynomial. The question tells you it's unique, so you must have gotten the correct one somehow. But right now it is not monic, right? Because if you look at the x power 67 term, there's 67 here, there's 1 there. So when you reorganize, you need to do what? You need to remember later on, I want to actually divide by a 66. Right? Divide by 66. Now, what is the x squared term? What is the coefficient here? Well, there's not going to be anything from the left-hand side, so it's only from the right-hand side. And when you expand the right-hand side, you need to use the binomial theorem. So this number here will be exactly 67 choose 2. So therefore, when you actually go and do the value of x power 67, we have to do what? We have to do 67 choose 2 divided by 66. So A is exactly 67 choose 2 divided by 66. If you calculate out what that is in fact 67 over 2. So the answer is absolute value round down 33. Okay, question number 22. If you, okay, I hate this question. Okay, this is such a troll question because of the condition given in the question. Believe me, when I said I spent a few minutes on this and was thinking about actually how to use this. Because what does this remind me of? At first, I was thinking, hey, this is like some combination of Stewart's theorem. But then I take a look at this condition, and then maybe like, hey, this is something you can use Ptolemy's theorem on. But actually, this is nothing. You can just completely ignore this question. How come? Or rather, this condition. Because you don't need to find these three lengths, right? DE, EF, FD, they don't actually matter to you. The thing that matters is the fact that this is true. And when this is true, what that means is that the circle passing through F, D, and E is tangent to BC. And this is your alternate segment theorem. I think that's what they call it in schools. Does it pass through A? Well, we don't have to care about that. It doesn't really matter. Right. So let's say we draw the circle. Let me try to fit it through those 3 points. Maybe a bit hard. I'm going to try. Not perfect. A bit more. Good enough. So what we can do here is that the key thing here is to use power of a point. It's not to use the length condition given in the question. So power of a point says that BF times BA is equals to BD squared. So if BF is equals to 8, AF is equals to 24, then BD squared is equals to 8 times of 32. So BD must be 16. On the other side, CE times CA is CD squared, CE is 9, AE is 16, so CD squared is equals to 9 times 25, right? So CD is 15. And then we're done. Right. Then we're done. Oh, I just realized my screen was a bit too low, too high. You all cannot see my 16 and 15 I wrote down here. Okay, but anyway, the answer is 31. Let's move on. Question number 23, let n be the number of positive integers less than or equal. So very important. This means that you can include 1-digit number, 2-digit number. Okay, 1 digit cannot, right? 1 digit, this is not possible. But you can include like 2-digit number, 3-digit number, so on and so forth, 4-digit number, and finally 5-digit number. So what we can think of it as a number from 00000 to 99999. Right? Because I can add extra zeros, padding zeros at the front of the number, it doesn't actually affect the answer. Now, what do you do? Well, let's call them A, B, C, D, E. A, B, C, D, E, we know that they are all between 0 to 9. So one option is that if I'm trying to solve some kind of equation, A plus C plus D plus E, A plus B plus C plus D plus E equals 13, we can use our stars and bars. That's a standard idea. But because of the upper bound of 9, we can try to remove all those extra cases that don't actually work. So this one, if no restrictions, how many ways are there? If you're just given this thing, not saying no restrictions, just positive. Right? If it's just positive, don't have the upper bound. Then it's very simple. By stars and bars, we put 13 of this down, we put 4 dividers, we arrange them in a row. What do you have? Exactly 17 choose 4, right? If no restriction, if no restrictions. Yeah. But now you have to remove those that don't satisfy the condition. So what are those that don't satisfy the condition? Basically, you have 10 something 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 something, 11 something 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 something, 12 something 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 something, and 13 something 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 something. Last one, obviously, there's one way. Right? Or is there only one way? Well, it could be the second digit is the so-called 13, or it could be the third number is so-called 13, and so on and so forth. So later on, we need to remember to multiply by 5. Right? But for now, let's continue counting. What about this one? You have a 1 getting put in one of these 4 choices, so obviously that's 4. For this one, you split the number 2 across 4 numbers. If you split the number 2 across 4 numbers, that means you have 2 zeros and 3 dividers. It is a 5 choose 2. It is a 10. Here you split 3 across 4 numbers, so you have 3 stars and then 3 bars as well. So it's 6 choose 3. That's 20. So one group has 35 basically. But then now what we need to do is that we need to take the 35 and then multiply by 5, right? Because of the fact that this can happen not just to the first digit, but it can also happen to the second digit, third digit, so on and so forth. So 35 times 5. And then we just subtract it from 17 choose 4. Okay. I'm gonna skip over the calculation. You can see that this is just 2205. Okay. So question 23, not too difficult, right? As long as if you have enough patience, you can do it. Actually, same thing for 24 and 25. I'll say that question 23, question 24, question 25 are moderate difficulty. In fact, in this paper, they are considered easy compared to the rest of the questions we have. Here's 24. So the numbers here, where there are pairs of numbers from 0 to 10, are categorized as beautiful and ugly. Beautiful numbers are numbers where the two coordinates are equal. Ugly numbers are numbers where the first coordinate is less than the second coordinate. So 0, 1, 0, 2, 0, 10, right? 1, 2, and of course all until 9, 10. Now these are the only two things inside C, because C has a certain ordering. X must be less than Y. Less than or equals, sorry. So if it's equal, it's the first case. If it's less, it's the second case. Right? So these two things, they make up C. Now, what is the probability that when I choose two numbers, I have one beautiful and one ugly, but also I have one number in common? What's the probability? So an example of one of this outcome is 1, 1, and 1, 3. Here's the idea. No matter what ugly number you choose, x, y, there's only two ways to match the beauty number. It's either xx or yy, right? This is when you choose xy. So therefore, we just need to consider this case. Right? The total number of numbers is obviously 66 choose 2. But why is it 66 choose 2, by the way? Because there are 66 numbers here, right? 11 choose 2 pairings, 66. So there are 66 choose 2 ways to choose two numbers, or rather two elements from C. How many ways are there? One ugly, one beautiful, one number in common. So we first choose the ugly number. The ugly number can be any one of these 55 numbers. Right? So there are 11 here, there are 55 here. And then I mentioned before that to match this ugly number, there's only two ways. Either you match it following XX or you match it following YY, right? So that is the answer. Finish. So simplify 110 over 33 times 65. You can divide by 11 and 5. So that's 2, 3, 13. 2 over 39. So that's P. 1 over P round up will be equals to 20. Okay, finally, we are at the very end. Particle starts at the point 0, 0 and moves towards the point 8, 4, so that it moves either rightwards or upwards and cannot move 3 steps in the same direction. Now, when you see this kind of question, my first instinct is actually to do recursion. Because if you do recursions, this is a common type of question I've seen before. We have seen this question before in Sec 2, Sem 2 lesson. I forget already. But if you try recursion, you realize that it doesn't quite work for this question. Because recursion usually goes towards a point where it's n and n. I don't know, sorry, not n, n. It usually goes towards any point that lies on, for example, x plus y equals to 12. Right? Because recursion, when we do that thing, we only consider, for example, sequences of length, let's say 12, right? Sequences of length, let's say something. So this one wants us to land at a very specific point 8, 4, where we know that there must be 8 rightward movements, there must be 4 upward movements. You cannot possibly use recursion for this. You have to just count manually. By the way, one idea for this question is also maybe there's some kind of like just plotting out the xy coordinate and just go and counting them, but that one is way too tedious, not recommended at all. So how many ways to do this? Firstly, can you have 3 U's in a row? The question tells you no, right? But if you have 3 U's in a row, automatically you also have 3 R's in a row, if you think about it. Because let's say you have 3 U's in a row, this is, let's say, one block, let's say there's another U, right? The 8 R's, where must they go? Maybe you put them like this, but even if it's like this, you can see that there must be 3 R's together. So here's the fact. As long as there are 3 U's, there are 3 R's together. So cannot, right? Cannot. What happens when there are 2U's together? Let's explore this case. When there are 2U's together, then you see, this is actually possible, right? When there are 2U's together, you can see that there can be actually only one case here, RR, 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 and RR. So this one will give a total of 3 of them. Okay? So this one will give you a total of 3 of them. And then now, what we can do is that we can now continue, right, with the case where you have 4U's separating. Okay, later I'll tell you actually why I don't like this case. You will see why later on. So the last case is where all the U's are separate. Then how many ways to put them in? The number of ways to put them in is you need at least one here, at least one here, at least one here, but you can have at least 0 here, right? In fact, you can actually combine these two cases into one single step in your working to make your work a lot easier. Let me show you how. Since we don't care, since we never get the 3U's together, it's fine. We can just do it like this. And the consideration here is that each of these boxes can have from 0 to 2R's. 0 to 2R, right? So what are the possible cases? In fact, there's only 2 of them, 2 types. It's a 22220 or it's a 22211. For a 22220, it's inclusive of basically the case we have 2U's together, right? Like we discussed just now. But it's also inclusive of this kind of things, where we don't have 2U's together. So in fact, we can absorb that other case into this case to make our life easier. For 22220, in fact, it's quite easy to see that there's only 5 ways, right? Whether the 0 is here, whether the 0 is here, whether the 0 is here, here, here. For the 22211, obviously 5 choose 2 ways because you only care about where the ones end up, right? And automatically the remaining ones will have 2R's. So total, 15 ways. Finish. So surprisingly, not a lot of ways. And in fact, it's quite small number of possible paths. Anyway, that's the final answer. Good luck for any one of you taking the SMO Open tomorrow. In fact, if you're taking it tomorrow, you shouldn't even be watching the review right now. You should just be resting. I don't know why you'll be watching it now. Anyway, yeah, that's all. See you tomorrow at the same, not the same time. Sorry, at 6. Wait, what time did I set my schedule? Let me check again. My schedule is 6:30 p.m. tomorrow. Okay. Yeah. Bye bye.